So today we'll be studying the chapter Electromagnetic Induction. It is quite an important chapter of physics of the 12th class. We studied after magnetism and electricity and capacitance. And this chapter basically involves a lot of integration and mathematical calculations. And once you visualize how exactly you are to do the part of this flux, it's not a very lengthy or a very complicated chapter. It doesn't give you much scope for questions. There are much direct questions because there is not much scope for turns and twists in this chapter. So actually it is a quite scoring chapter once you do it thoroughly and once you are clear with the concepts. So okay, today we first of all we start with the theory for the chapter Electromagnetic Induction. So here it goes.
See, before starting this chapter, I will give you a brief idea about flux. You all would have heard about flux. You have dealt it with in the magnetism part. Flux is nothing but the number of magnetic lines of force which are passing to a closed area. For calculating flux, you must check whether the field and the area are in the same direction or not. The flux equation can be written as integration of B dot dA. I am giving you a simple example to determine the flux. See, in this example, we are going to calculate the flux linked with this ring. This ring is placed in a magnetic field. And this ring is placed in such a way that magnetic field is passing magnetic field is
going into the
paper.
Exactly, the cross dot here, we know that the dot thing point means that the field is coming out of the paper, while the cross signifies that the field is going into the paper.
Here the B vector and the A vector are both parallel to each other. So B dot dA is the dot product will give the maximum value, because the angle between them is 0 degrees. So B into dA vector into cos theta, and the theta is 0 degrees. So it will produce maximum amount of flux.
So basically we would say that for plain closed figures we simply use the formula for the area, that is the change in the area through which the flux is passing. And be it as it is a simple closed figure, though, so the field will be passing the entire of its area, that comes to be pi r square simply.
So it's nothing but B into pi r square, because these both are perpendicular. It is a simple integration, as B is constant and area is also constant. So the answer will be pi r square B. To calculate the EMF, we need to know about the Faraday's law. Faraday, he observed that the change in magnetic flux causes the current to flow in the circuit. There is nothing but developing the EMF. And he observed that it lasts as long as there is a change in flux. So it means that if there is a change in flux, there is current flowing in the circuit, that is EMF is developed. So by this, he gave a relation that the EMF is nothing but the rate of change of flux, and it is minus d phi by dt. Exactly. So it means that it opposes the rate of increase in flux or decrease in the flux.
So basically हम कहते हैं कि जब तक flux change होता रहेगा, that is rate of change of flux जब तक zero नहीं होता, d phi by dt, we would have a non-zero value for the electromotive force that would cause the current to flow in the circuit, developing EMF. और ये जो EMF होता है, इसका direction, this will be the negative of the rate of the direction of the change in flux, because it is meant to oppose the direction of the cause that actually produced it. So next we come to the Lenz's law.
Lenz's law. I said you earlier, right? The EMF developed will always oppose the rate of change of flux. So Lenz has said the same statement. He said that the induced EMF opposes the rate of increase or decrease of flux. So if the flux is increasing in the anti-clockwise direction, the EMF will be induced in the clockwise direction to oppose it. You will always try to oppose the direction. And in the same way, if it is decreasing in the anti-clockwise direction, then the EMF will also be will be induced in the anti-clockwise direction only.
That's right. So we now talk about the motional electromotive force.
When a rod is moving in a magnetic field, what will happen with some velocity? There will be some EMF induced within the rod. Let us see how. See, it is given by formula integration of V cross B dot dl. We'll go to the next topic. I'll explain you about this formula in a given example. I'll consider a rod of length L which is moving with velocity V.
That's right.
And it is placed in such a way that the magnetic field is perpendicular to the rod. So if it is moving in such a way, first let me consider a dx part of a rod placed at a distance h from the bottom over here. Every part of the rod is moving with velocity v. Even this dx part has a velocity v. And the EMF induced in the small part will be v cross b dot dx. And the velocity and the magnetic field are always perpendicular, right?
That's right.
So v cross b is always v into b.
Also, we know that had it been parallel, we know that V cross B is V into sine theta, its magnitude. So, had it been parallel, the value of sine theta would have been 0 and simply our EMF would have turned to be 0.
And again, V cross B is parallel to dx. So, this would give out a maximum value. So, the EMF denoted by the small area dx would be VB dx.
And we integrate this dx from 0 to L obviously for the length of the rod. So on integrating we find out that it comes out to be V into B into L.
The flux can be changed by two methods. Flux is nothing but B into A, right? So the flux can be changed by changing the B or by changing the A. If B is changed, that nothing but the magnetic field is changed. So what will happen is there will be an induced electric field. See, this is called, this induced electric field will be in closed loops.
That's right.
For example, if B is changing as a function of B naught into T, if it is changing linearly with time, there are two relations to find out the induced magnetic field at a distance r. And if we consider a closed loop which consists of the magnetic field B which is changing at the rate of B naught into T, and if we consider that there is no magnetic field outside this region, inside the region you would find that the electric field, induced electric field would be B naught R into R by 2. It would be linearly increasing with the radius, distance from the center of the circle.
That's right.
But if you go to the area outside this region, there will be an induced electric field. But this induced electric field will linearly decrease with after R. And this induced electric field would be V naught into R square by 2R. And if you plot the graph, it would simply look like this. Till from 0 to R, it will be linearly increasing, and after R, it will be gradually decreasing.
That's right. So basically this is an important graph of ER.
And the induced electric field will form concentric circles. The normal electric field will never be concentric, will never form concentric circles. That is conserved. This is not a conservative force. This is an example of a non-conservative force.
That's right. Let's now move on to self-inductance, that is L.
If I is the instantaneous current in the coil and flux linked with the coil is phi, this phi is directly proportional to I, and this proportionality and phi is given by some constant into I, and this proportionality constant here is called self-inductance.
Exactly. So we can also define self-inductance by a formula.
So we can give that the self-inductance as phi by I.
That is also given as mu naught n square a by L, which is very intuitive. By just putting the values, we get this value.
And if we see this relation phi equal to L into I, we can also differentiate this relation. Then if we differentiate this, we will get minus E is equal to L into di by dt, and this E is called the EMF developed in the coil.
Exactly.
And this is directly proportional to the rate of change of current.
Current, that's right. So next we see that for solenoid also, for example, the self-inductance, we have the formula for L to be mu naught n square a by L, right?
Where n are the number of turns of the solenoid, L is the length of the solenoid, and A is the area of cross section.
Exactly.
These are the terms.
Exactly.
To remember.
So now we move on to mutual inductance, that is capital N.
In the similar way, because of current in one coil, there will even be flux induced in the other coil, which is present at some distance away from it.
That's right.
If we consider two coils A and B, if we consider there is a current IA in the coil, and because of this current IA, there could be flux phi B induced in coil B, and this phi B can be directly proportional to IA, and the proportionality constant is called mutual inductance of these both coils.
That's right. Exactly.
And the mutual inductance of the coil A with respect to B is also equal to the mutual inductance of coil B with respect to A.
That's right. It is because as by the name only, it is mutual inductance, right? So we get basically that phi B is equal to MBA into IA being the current through the A wire. Okay. So this was about the mutual inductance.
Inductance. See, just like the resistors, if we connect the inductors in series and parallel, we can find their effective inductance.
Exactly. So
you can just compare the inductor with a resistor in this fashion. See, if inductors are connected in series, that means if one inductor is connected to other inductor n by n, the effective inductance will be added. That is nothing but L effective will be L1 plus L2 plus L3, just given in the diagram.
That's right. So basically we see that just as we calculate the equivalent resistance for series and parallel thing, similarly we can and also the capacitance. In the similar way we can find the equivalent inductance in series and in parallel circuit when many inductors are placed in the given fashion. So basically, isn't it important to go through the derivations of these formulas, like how we derived the formula L1 plus L2 plus L3 for L effective in case of series and the sum of reciprocals in the parallel case?
No, the derivation is also the same like the derivation of the resistors. There is no much difference, and it is actually not much useful also. We in the IIT JEE they will just ask the questions like the effective inductance or effective resistance.
Okay, that's right. So basically there's no point of wasting much time going into that thought. Okay.
And the energy stored in an inductor is given by half Li square.
Okay.
And this derivation is also required, but you must go through it. This is used in many places.
Okay. So we move on to growth circuits now.
Growth circuits are nothing but the circuits where the current increases slowly. See, if an inductor is connected to a resistor in a normal circuit, the current doesn't increase suddenly. See, if a inductor is not removed, the current would be E by R.
That's right.
And this E by R would come instantaneously as soon as the switch is connected. Now, because of placing the inductor, what happens is the current will increase slowly and finally reach in a steady state where the current will become E by
Basically,
R.
we say that this is a property of an inductor that it does not allow current to across it to change within no time. Basically, current across an inductor cannot change instantaneously. And this is very similar to the capacitor. We say that for capacitor, the charge across a capacitor doesn't change instantaneously. In a very similar way, the current we say across an inductor remains constant at a given point of time.
Actually, it increases slowly, but it takes some time.
That is, we take it to be negligible to save the tedious calculations, and using those assumptions, we like put those assumptions in our question to solve it further.
See, the potential difference across the inductor will be L into di by dt, and potential difference across the resistor will be I into R.
That's right.
And this would be equal to the potential difference across the
Battery.
That's right. If we solve this equation, we will get I of t as E by R into 1 minus E power minus RT by L.
Exactly, and that is a very important result. In fact, that is a direct equation.
If you plot the graph, this would look like this. If you reach the steady state after very long time. So, in this way, the inductors are important to increase the current slowly.
And what is the maximum limit of the value in the graph that it tends to?
It will be E by R. It will reach E by R at infinity time.
Exactly. We can say we can see this from the equation also. If you just put
tend to E by R.
t tends to infinity, limit t tends to infinity, you can easily say that the inside the bracket the term of the E will just tend to 0, and we could say that in that case it tends to E by R. So it approaches, we could say that current approaches the value E by R as time tends to infinity. So basically we say that this is a graph of the inductance and this is the equation. Okay.
Consider this diagram. Initially, the switch S1 is closed and S2 is open. So what happens is the current gradually increases and finally reaches the steady state where the current would be E by R. Later, after the steady state is reached, now the S1 is closed and S2 is open. Now then what happens is the battery is disconnected from the circuit.
That's right.
Only the resistor and the inductor are present in the circuit. Generally, if the inductor is not there, the current will automatically become 0.
True.
But because the inductor is there, it will oppose the decrease in current. So what happens is the current starts decreasing gradually. It doesn't become 0 instantaneously.
Right. So
see, if we close the switch S2 after reaching the steady state, the voltage across the resistor will be I into R, and the voltage across the inductor would be minus di by L di by dt.
right.
If we solve this equation, we will get I at any time t will be E by R into E power minus RT by L, and this graph would look like something like this.
Exactly. And in this, what will be the minimum value?
Minimum value it will be 0 and will reach 0 at infinity. And see, if the inductor is not there, the current falls to 0 instantaneously. Here, because of inductor, the current is decreasing gradually and finally reaches 0.
That's right. So basically we see that this is a difference, this is a decay current, and the formula, the expression for I with respect to time, that is current, and in terms of time is different, as in before case it was E by R into 1 minus E to the power minus RT by L, but here it is E by R into E to the power minus RT by L. In fact, the graph also we see that is it is inverted in shape. Okay, that was reaching a maximum value, this actually tends to reach a minimum value. So next we move on to alternating current, that is AC circuit we also call it.
Here we are dealing with circuits where the EMF is varying with respect to time. For example, we'll maximum deal with the circuits where the EMF varies sinusoidally. That is, the EMF would be as a function, would be a sine function or cos function. If we consider this case, here the voltage is given by V0 into sin omega t. This is a sinusoidal function. Here the current would be also a sinusoidal function. If it is connected to a resistor, the current would be simply I0 into sin omega t.
That's right. So basically it will be fluctuating with time as a function of in the form of sine omega t.
Yes.
So basically this is the introduction to alternating current, and in this we basically see that the current is V by R into sine omega t, and that is we could also say it I naught into sine omega t, where I naught is V by R, that is at the initial condition.
Where I0 is the maximum current.
Exactly. So basically we see the case 2 now. In the previous case we saw that the circuit had a simple resistor connected to it, okay, and with V is equal to V0 sin omega t obviously, and in this case we have a capacitor connected in the circuit. So how will we proceed in this case?
In this case we are having a capacitor. Here we know that the voltage across the capacitor is given by Q by C. Q is nothing but a charge stored in the capacitor, and C is the capacitance of the capacitor. If we consider see this equation, V is changing with respect to time. V at any time would be V0 sin omega t, right? And Q at any time would be Q C into V0 sin omega t.
That's right, because we know that the charge is C into V, Q is C into V, right?
This Q is nothing but di by dt.
That's
so,
right.
If we take dt towards the other side, and if we integrate this equation, we will get IC is equal to
I naught sine into omega t plus phi by 2. That's how to derive the equation.
And this I naught is nothing but V into C omega.
That's right.
So, and we find that V is a function of sine, right? V is nothing but V naught into sin omega t. But we find IC is a function of sine into omega t plus pi by 2.
That's
and so the
right.
phase of the V voltage at any time would be omega t, but the phase of the current in the across the capacitor, we find that it is pi by 2 phase. It leads the voltage of the across it by pi by 2.
Okay, so basically, okay, that's right, we derived this equation, the expression for it, and we don't need to blindly memorize it. Deriving it 1 or 2 times will obviously make us memorize it automatically. So,
Simple in derivation first.
Exactly.
And afterwards, we'll proceed to case 3,
Okay.
where the battery is connected to an inductor. Here the current, the inductor, what we all know the function of inductor, it always opposes the current. It decreases the rate of change of current, right?
That's right.
So the voltage across the inductor at any time would be L into di by dt. And if we integrate this, we will get current across the inductor as V naught by omega L into sin omega t minus pi by 2.
That's right. So we see that we have derived the expression for voltage in this case. The current in this case in terms of inductance, right?
And we find that the phase of the current in the inductor is lacking the phase of its voltage by pi by 2.
Exactly, because we saw that for voltage the phase is omega t, but for the current it comes to be omega t minus pi by 2. So that's right, we derived these equations. We saw 3 cases, one being where a simple resistor is connected, second being where a capacitor is connected, and the third being where L is connected. So is there any rule to how should we remember who's going to leave who in what case? Because okay, that's good, we'll derive it and it's not a very difficult thing, but we won't really be having the time every time to just sit and derive the equation.
It's a good question. When it is connected to a resistor, both the voltage and the current will be in the same phase.
That's right.
But you can just remember in this way, such that ICE and ELI, such that if it is connected to a capacitor, the current in the capacitor leads its voltage.
Right.
And similarly, if it is connected to a inductor, the voltage across the inductor leads the current in it.
That's right. That's right. So basically, okay, yeah, we could use that Iceman thing and that Ailey thing. Okay, so in fact, I think even if you remember one of them, that is Iceman. Okay, if you know that current leads the voltage in the capacitor, so it is obvious that the voltage is going to lead the current in the inductor.
Yes.
And moreover, even if you forget, in any case, you can always derive it. It's a very small and easy derivation, right?
Here we see all the three. The inductor, the capacitor and resistor are directly connected in series to the voltage, which is varying sinusoidally. So we immediately get it out what to do in this case.
That's right.
We can observe directly that a common current passes through all the three, right? Through the inductor, through the capacitor and through the resistor, always the same current flows.
Because we know that they are in series connected in the circuit.
But the voltage across these will be different. For example, the voltage across the resistor and the current both will be in the same phase. But across the capacitor, the voltage lags the current, right?
Right.
And in a similar way, the voltage across the inductor leads the current. So
That's
we have
right.
the current in common, but the voltage that's across the resistor, inductor and the capacitor are not in the same phase.
That's right.
The voltage across if we think the voltage across the resistor is in a phase phi, the voltage across in the capacitor would be pi by 2 phase more than the resistor. And similarly in the inductor will be pi by 2 phase lesser than the resistor. So in this case, what we do is, as they are not the same, we can directly the derivation of this is big hectic. So I will directly say that voltage, the total voltage at any time would be V of t, right, which is V0 into sin omega t, would be nothing but would be given as under root of VR square, voltage across resistor plus voltage across inductor minus capacitor whole square.
Exactly. So we could also see that this is just like a right angle type of a property. Basically it being the root of VR square and
Yes.
plus the difference of VL minus VC and the whole square of that.
Yes, I can compare it to sides of a triangle where each varies by a phase phi.
Exactly.
And we'll introduce a new term Z, which is called impedance. This is nothing but under root of R square plus XL square minus under root of R square plus XL minus XC whole square, where XL is omega L and XC is 1 by omega C. I have mentioned you about the term XL and XC in the previous slide, where XL is the effective resistance of the inductor and XC is the effective resistance of the capacitor. And I will introduce a new term phi. This phi is nothing but the phase by which the current lags the voltage across the whole circuit. This tan phi is given by this relation 1 omega L minus 1 by omega C by R.
That's right.
And this cos phi is given by R by Z, where Z is impedance and R is the
Exactly.
resistor.
And we know that omega L being the impedance in case when the circuit has pure inductor, and 1 by omega C being the impedance when the circuit has a pure capacitance.
See, if omega L is greater than omega C, tan phi is positive. That is nothing but phi is positive. If phi is positive, the current, the voltage across this leads the current, because the current is given is phi phase lesser than the voltage.
Right.
In the similar way, if omega L is less than 1 by omega C, tan phi is negative. If tan phi is negative, the phi is negative. So here the plus sign will come and the current will be ahead of the voltage.
That's right. So basically, we can just draw several cases from it, that if we know that impedance of the inductor comes to be greater than impedance of the capacitor, we say that the voltage leads current. Okay, so because we obviously know that in case of an inductor, voltage leads current. Similarly, we come to the cases, the second case also, and lastly we say that if omega L and 1 by omega C are equal. Okay, so that is the condition of resonance, when none of them leads or lags each other.
I'll explain you this case resonance. Generally, the maximum current in the circuit is given by I, which is the V by Z, where Z is called impedance, and Z is nothing but under root of R square into plus XL minus XC whole square. And this Z will be minimum when XL is equal to XC, and if Z is minimum, the I will be maximum. So the maximum current passes through the circuit when XL is equal to XC, and if when this condition took place, this is called resonance. If XL is equal to XC, 1 by omega L equal to 1 by omega C, then the omega will be under root of LC. So this omega, when it becomes under root of LC, it is called angular resonance frequency.
That's right.
And during resonance, power dissipated in the circuit will be maximum. Power dissipated in the circuit in one cycle is given by Vrms into Irms into cos phi. In resonance, cos phi is nothing but R by Z.
Exactly.
In resonance, R is equal to Z and the power dissipated will be maximum.
Exactly. So basically this was all about alternating current, and with this we come to an end to the theory of the chapter electromagnetic induction and alternating current. We'll now be looking at some good questions and trying to cover even more of the theory and some important concepts that are important from the competitive exam of you. Okay.